Hi everyone, I'm Rohan Sahani from Carnegie Mellon, and in this talk, I'm going to revisit the classic problem of conformal or angle preserving flattening and show how, with the proper treatment of boundary conditions, it becomes a powerful and modern tool for surface parameterization. In particular, I'll present the boundary first flattening algorithm that enables real time editing of high resolution maps with minimal area distortion, direct editing of boundary lengths or angles, exact preservation of sharp corners, seamless cone singularities, and maps to arbitrary target shapes. More broadly, since the target shape can be updated efficiently, BFF now provides a new paradigm for conformal parameterization. Rather than waiting for a single predetermined flattening, one can interactively edit or optimize maps with hundreds of thousands of elements. Moreover, its ability to generate high quality maps efficiently makes BFF a drop in replacement for widely used schemes like least squares conformal maps. Our initial motivation for this project was to explore the space of conformal flattenings efficiently, which we managed to do. But in the last year or so of playing around with this algorithm, what we've also found is that it's surprisingly robust. In particular, BFF's ability to specify explicit boundary conditions sets it apart from other linear methods in providing well behaved solutions. But before I proceed any further, let me first motivate why conformal maps are a particularly good choice for surface parameterization. In the past decade or so, conformal flattening has really grown beyond its initial applications in texture mapping to now providing new perspectives on a range of topics from machine learning to 3D fabrication. In fact, several papers presented at this year's SIGGRAPH use algorithms for conformal flattening as a basic building block. So, why such an interest in maps that preserve angles? Well, it turns out that it's often possible to do just as well as nonlinear schemes in terms of quality, but at a fraction of the cost. Computing a conformal map amounts to solving easy linear equations, which in turn results in fast and scalable algorithms. Okay, but what's so special about angle preservation? Aren't there a whole bunch of energies that trade off angles and scaling to better minimize distortion? Well, it turns out that there's no magical energy that completely eliminates distortion. All parameterizations suffer from either angle distortion, scale distortion, or a combination of both. Instead, the choice of cuts turns out to be far more important to compute a near isometric map, with conformal energies typically being the cheapest to minimize. However, current methods for conformal flattening have two major shortcomings. First, existing linear methods provide no explicit control over the boundary. The user obtains a single automatic flattening and one must take it or leave it. I'll address this issue in this talk. Second, conformal flattenings can exhibit significant scale distortion. To deal with this, the method of cone singularities has recently become popular. In fact, a recent work by Solomon and colleagues builds off some of the mathematics presented in this work to now solve this problem optimally. Since the related work on surface parameterization is quite big, I'll focus specifically on conformal methods, starting with the so-called free boundary methods. Here, LSCM and ABF are classic techniques that approximate the Cauchy-Riemann equation or angles in the input mesh directly. Unfortunately, none of these methods address the question of boundary control, and instead opt for so-called free boundary conditions by minimizing a discrete energy without any explicit constraints on the boundary. So, although these methods provide a unique solution, that solution ends up having no meaningful interpretation in the smooth setting. In the absence of explicit boundary conditions, there's an enormous space of perfect conformal flattenings, obtained by flattening and then applying in-plane conformal maps. This then further suggests that the solution chosen by free boundary methods must depend on the discretization, meaning that results will change based on the particular choice of mesh or numerical treatment, as shown by previous work. Now, a first attempt at getting a desired shape might be to pin all the boundary points. However, This approach generally results in maps with severe angle distortion, since a compatible conformal map might not exist. Later methods explicitly incorporate boundary conditions. Here, CETM serves as the gold standard, providing high quality maps with control over both boundary lengths and angles. Unfortunately, this approach requires expensive nonlinear optimization. Compared to previous work, then, BFF turns out to be faster than existing linear methods, yet provides quality and control comparable to sophisticated nonlinear schemes. I'll now dive into the details behind boundary first flattening, starting with the smooth theory. The key idea is pretty simple. If you know the boundary of a conformal map, then its extension to the interior is easy. The details take a little time to work through, so let me start with a high level sketch of the algorithm. First, we ask the user to specify either the boundary scaling or curvature of our target map. Then, we solve something called the Yamabe problem to get the complementary curvature or scaling along the boundary. We now integrate this information to get our boundary curve, and finally extend the solution to the interior via a pair of conjugate harmonic functions. Let's first discuss the Yamabe problem to compute complementary boundary data. In general, it's not true that any parameterized curve describes the boundary of a conformal map. The curve has to satisfy certain conditions. In particular, the Yamabe equation provides an explicit relationship between a scaling of the metric and the associated change in curvature. Here, U is the conformal scale factor, while K and K tilde are the Gaussian curvatures on the original and target domain. The boundary conditions for the Yamabe equation were studied by Pascal Cherrier, but for some reason have been omitted in the literature. This equation provides an important missing link, as it also relates the conformal scaling and the associated change in curvature, but this time along the boundary. Together, these two equations tell us that a conformal map is uniquely determined by prescribing either the scaling or the curvature along the boundary, but not both. So, if you know one of these quantities, then solving the Yamabe problem determines the other. A key step in BFF is recovering a closed boundary curve using information from the Yamabe problem. Luckily for us, boundary curvatures and scaling uniquely determine a closed curve up to rigid transformation, with the cumulative curvature telling us how much to turn and the scaling giving us the speed to move at while we draw the curve. Okay, now that we have the boundary of our conformal map, how do we actually determine the solution on the interior? Here, we turn to an alternative representation of conformal maps in terms of conjugate harmonic functions. Say A and B are two real components of a conformal map F, then this formulation says two things. First, that the gradients of A and B must be orthogonal with equal magnitude, and second, that A and B must be individually harmonic. That is, the Laplacian of these functions equals 0. If F is conformal, then A and B are set to form a conjugate harmonic pair. To compute a conformal map, we proceed by fixing either A or B along the boundary and minimizing a conformal energy with respect to the other. Okay, with the smooth formulation of our algorithm now in place, let's discuss how to discretize it. We discretize our surface as a manifold triangle mesh with this topology and work with standard quantities in geometry processing such as edge lengths and angles. As is usually the case, we define angle defects at interior vertices and exterior angles at boundary vertices over their respective dual volumes. Let's again start with the Yamabe problem. The first thing to notice about the smooth Yamabe problem is that it's nonlinear. So, to avoid solving this difficult problem directly, we instead integrate these equations over their dual volumes to get linear relationships. Here, A is just a standard cotangent Laplace matrix, omegas represent the source and target angle defects, H is the discrete Neumann boundary data, and K's are the source and target exterior angles along the boundary. Since we're flattening, we can set the target angle defects to 0. As in the smooth case, we prescribe either exterior angles or scale factors along the boundary, but not both. So, how do we switch between angles and scaling if we only know one of these quantities along the boundary? Well, rewriting the Yamabe problem in block matrix form and partitioning the interior and boundary vertices makes it easier to see how this can be done. In particular, it helps us identify a pair of Poincaré-Steklov operators to convert one type of boundary data to another. For example, the Neumann to Dirichlet map takes boundary angles as input and solves the block system above for scale factors. Boundary scale factors are then simply read off from this solution. The Dirichlet to Neumann map, on the other hand, takes boundary scaling as input and solves the Dirichlet problem in the first row of this block system for interior scaling. A little bit of algebraic manipulation then gives us an expression for target angles. Amazingly, these angles exactly sum to 2 pi and automatically satisfy the discrete Gauss-Bonnet condition. To construct our boundary curve, we first rescale boundary edges of the input surface using scale factors from the Yamabe problem. Unfortunately, an extremely small discretization error prevents our boundary curve from closing. So, we formulate a small least squares problem to adjust only these rescaled edge lengths to close the curve. Since exterior angles are exactly preserved, we obtain our target boundary by simply integrating scale tangents. Finally, to extend our boundary curve to the interior, we fix one of its coordinates and minimize a discrete conformal energy with respect to the other. In practice, this leads to performing a harmonic extension on A and solving a Neumann problem for B. Here, another Poincaré-Steklov operator called the Hilbert transform is used to map the tangential derivative of A to the normal derivative of its conjugate pair, B. We derive a simple expression for this Neumann boundary data, which is as conjugate as possible in the least squares sense. Okay, with the core BFF algorithm now in place, the essential question becomes how to devise boundary data suitable for a variety of mapping problems. Let's first start with the case where the user provides no boundary data. In this situation, we simply pick the flattening with minimal scale distortion. We obtain this automatic flattening by prescribing constant scale factors along the boundary, as suggested by Springborn and colleagues. Here, BFF produces results that are virtually indistinguishable from the nonlinear CETM approach, while respecting details such as symmetry better than LSCM and spectral conformal parameterization. For interactive editing of angles and lengths, we use a spline-based curve editor. Here, we non-rigidly pack charts into a textured atlas while remaining conformal. Next, to get target shapes with sharp corners, we harmonically extend both coordinates of our boundary curve to exactly interpolate its angles. Since our boundary curve is already very close to being conformal, this procedure converges to a conformal map under refinement. Now, as I had mentioned earlier, cone singularities are a powerful technique to mitigate scale distortion in conformal maps. The idea here is to first map to an intermediate surface that's flat everywhere except for a few cone points. Then, to cut through the cone points and to finally lay the surface out in the plane without any additional stretching. This procedure can be incorporated into BFF with minor modifications to the algorithm. We now solve the Yamabe problem with a modified source term containing cone angles. Then, we cut through the cones, prescribing scale factors we just computed along the cut. The rest of the algorithm proceeds as usual and results in maps that are seamless by construction, allow interactive editing of cone angles, and again are virtually indistinguishable from CETM. Finally, we provide an iterative procedure for mapping not just to a circular disk, but to any arbitrary target shape. Now, I won't go into the details here, but I will mention that simply prescribing exterior angles along the boundary doesn't work. This is because there's several polygons associated with a single set of exterior angles. To uniquely prescribe a target shape, what we really need to control is the change in angle per unit length. But this turns out to be difficult to do algorithmically, since final lengths depend on scale factors which we don't know a priori. Therefore, we resort to an iterative procedure. I've already shown that BFF produces maps with quality comparable to nonlinear schemes. But it turns out that even in terms of performance, BFF is faster than current methods, including linear ones. In particular, it's about twice as fast as LSCM to obtain a single flattening, and an order of magnitude faster than that to edit the flattening. Why is BFF so fast? Well, the first and most expensive step of this algorithm is a single sparse Cholesky factorization of the Laplace matrix. The factorization of the Dirichlet problem is extracted at virtually zero cost from the upper left block. All subsequent problems are now solved efficiently via back substitution at a fraction of the cost of factorization. Under refinement, our method converges to a perfect conformal map at the same rate as all other flattening methods, but with the smallest maximum distortion on average. Finally, I had mentioned earlier that BFF has turned out to be surprisingly robust in our experience. We think this is for two reasons. First, we provide a principal discretization of the Poincaré-Steklov operators that guarantee exact integrability of exterior angles. This is not the case with finite differences. Second, integrability of edge lengths only needs to be enforced along the boundary. In contrast, previous work enforces integrability of lengths or angles over the entire domain, and as a result, suffers from artifacts. Now, injectivity is a topic that's attracted a lot of attention in the community recently. Unfortunately, BFF provides no guarantees here, other than strong empirical evidence showing that maps are usually injective. For example, on the Shrek 2011 dataset, only 6 out of 600 meshes had 1 to 2 flipped triangles each. On the more difficult Miles and Zorin dataset, only 5 meshes had more than 1% of the triangles flipped. In fact, these figures from the datasets are highly representative of the few rare cases where we do observe flipped triangles. While guaranteed injectivity is definitely valuable to have, it also comes at a cost. Editing a map can be hundreds of times slower with injective methods. A best of both worlds solution, then, is to first try a fast method like BFF and fall back if necessary. Lastly, we've released a really nice implementation that you can find online by Googling boundary first flattening. I'll now give a short demo of our app that comes built in with most of the functionality I've described here today. So, when I boot up the app, I get an automatic flattening with minimal area distortion. I can now edit that flattening along the boundary. So over here, I'm changing the scaling along the boundary, and here the curvature of the boundary. I can also prescribe cone singularities and edit those cone singularities, the cone angles, interactively. There are other nifty features built into this app, so I really encourage you to try it out. And that's it. Thank you for listening.